Hello, good afternoon. My name is Jacob Dayan, and today I'm going to talk about Lab 2 from Physics 2211 that talks about Newton's second law. So first of all, we'll talk about the motion of a falling object and its measurements and how the forces are acting upon the object while it is falling. Our purpose is to compare observations with two computational models with GlowScript and with the tracker application. Also, at the end, the experiment with gravitational force and drag force was more accurate than the one with gravitational force only. Additionally, it is very important to recall the fundamental principles of this experiment. First of all, as we said earlier, the experiment's topic is Newton's second law, and when an object is falling, it means that its net force is zero. Why? Because when an object is falling to the ground, the gravity is acting upon it, against it, with a negative acceleration, which basically slows down the object. So this tells us that the object falling to the ground has a non-constant velocity since it is slowing down. And this indicates a change in net force. Also, as we can see, we have different formulas as the one of gravitational force, the gravitational constant, and the drag force constant, as well as the velocity and its direction. As I said earlier, there are some forces acting on the object while it is falling. First of all, we have the force of gravity, which is a negative acceleration against the object. We also have the object's weight, which is its mass times its acceleration. And we also have the drag force and the air resistance that act as a frictions when the object is falling. Now for the video tracker analysis, I went to the library here at Georgia Tech, and I simply just dropped an umbrella to the floor and filmed it and used the tracker application to get the data. As we know, the system is the umbrella, while the surrounding is the library and the earth. Here I'm going to play the video. And as you can see, the dots from the falling object, they become more spaced. Is because the object is getting closer to Earth. Okay, great. So now I'm going to talk about the GlowScript analysis. To the left, you can see one of the pictures of my code where I simply just stated the objects from the program, which is basically the ball, its origin, and the trail it's going to run, and as well as the graphs of position versus time and velocity versus time. To the right, you can see, first of all, I set the time from the tracker analysis. And then I said the force, and in this case the only force acting on the object for comparison is the ball times its mass times gravity and its direction, which is basically the only force acting on against the object. And as well as I stated the velocity object formula as well as the position object formula, and we're gonna compare the results from the tracker video. Okay, so now I'm going to compare the experimental model versus the computational model. In this graph, you can see that there are three lines. The blue one comes from the experimental model from tracker, while the red and yellow come from the computational model of GlowScript. As you can see, the tracker video with the yellow one that both include some drag force are lined up very similarly. That is because in the real life, we do have drag force, unlike the red one where we simply just took it as negligible in the computational model. The reason why the lines are very spaced out is because the time intervals are very small. As you can see, it goes from 0 seconds to 0.2 seconds instead of a second per interval.
Now we're going to talk about the experiment essential question. So first of all, what does it mean? Which models, if any, predict a terminal velocity? So first of all, what is terminal velocity? Terminal velocity is the constant speed that a freely falling object eventually reaches when the resistance of the medium through which it's falling prevents further acceleration. So the model that predicts terminal velocity is the one that includes both gravitational force and drag force, as the forces act against each other and cancel out for a net force to be zero, meaning that we have constant velocity, which leads us to calculate the terminal velocity. Also, what if the object was initially thrown downward? Would the terminal velocity in this case be the same or different from the case where the same object was initially dropped from rest? So the terminal velocity will be the same, as it only depends on the velocity needed for the drag force to be exactly opposite to its weight, which will be the same in both cases. So the terminal velocity will be the same. Which in this case means that
Great, so thank you very much for paying attention to my presentation. For more information on physics, on Newton's laws, please subscribe to my channel, and thank you very much.